AB Calculus, section 3.6, day number 2. All right, we've got an example here where we've got a position function, t cubed minus 6t squared plus 9t. We're going to do a number of things with it, so let's get going. All right, part A says find the velocity. Well, the velocity is equivalent to the derivative of the position function. So v of t will be equal to the derivative of s of t. Therefore, v of t, using the power rule, would be 3t squared minus 12t plus 9. Okay, I'm going to actually simplify that a little bit further. I know what's coming, so it's going to make it a little bit easier. I'm going to take and factor out of 3. That'll be t squared minus 4t plus 3. And I'm actually going to take that even one step further, and I'm going to factor. I'm going to factor that trinomial, which will be t minus 3 and t minus 1. You can see where I'm going with that, but that's what I would call, you could call v of t any one of those three, right? That would be your velocity function, regardless of how you want to look at it. Okay, acceleration. Well, acceleration is the derivative of velocity. Therefore, I'd take my first velocity expression and take the derivative of that. And I'll call it a of t. So a of t would be the derivative of this function, all three actually, but it'd be easiest to work with that one. And I'll get 6t minus 12. I'm actually going to factor that as well, just so I can see where my acceleration will be equal to 0. Okay, again, either of these two forms would be fine for a of t. Total preference on your part, whatever you'd like to do. When is the particle moving to the left, and when is the particle moving to the right? All right, so the particle is moving to the left when v of t is less than 0. The particle will move to the right when v of t is greater than 0. So I'm going to sketch a graph of v of t. And I'm going to assume that time starts at 0. And v of t, I'm going to sketch based on this function of v of t. Now I know v of t will equal 0 when t equals 1 and 3. So v of t equals 0 at 1 and at 3. Now if you imagine, of course, v of t is a quadratic and it opens upward. So you can imagine what v of t would look like, without being exact with coordinates. Clearly v of t would be greater than 0 on these intervals and less than 0 in between 1 and 3. Therefore, the particle would be moving to the left between 1 and 3, and the particle would be moving to the right between 0 and 1, as well as any value after 3. Okay, now I have a justification there. It says, how do you know? Well, the how do you know part is my justification with the sign value of v of t. Okay, let's continue. When is the particle speeding up and when is the particle slowing down? Okay, so I'm going to do a comparison of v of t with a of t. All right, I'm going to do a little sketch of v of t, which I've already done. Okay, so 0 and 1 and 3. And I know that the particle is moving to the left, or the velocity is negative on the interval from 1 to 3. And I know the velocity is positive from 0 to 1 and from 3 and beyond. So I'll put velocity positive and velocity negative. Let's do the same thing for acceleration, and then we'll compare the two. Okay, so acceleration is linear. Right, you can consider either one of these. Now I know that acceleration will be 0 when t equals 2. Okay, so t equals 2 right there. It'll be equal to 0. So a line, you can imagine a line with a slope of 6 would mean that any value to the left of 2 would be negative. So acceleration will be negative between 0 and 2. And then it will be positive after 2. So what we're going to do is we're going to cross-reference the two graphs and see where they have the same sign and where they have different signs. Okay, so the particle would be speeding up. Speeding up when v of t and a of t have the same sign. Okay, let's determine based on our schematics here, or number lines here, when that would be. Okay, so I see same sign. Sign is negative between 1 and 2. Okay, so 1 and 2, as well as from 3 and beyond. Okay, so it's speeding up when t is between 1 and 2 and 3 and beyond. Okay, the particle is slowing down. That should be an S, slowing down when v of t and a of t are opposite signs. Okay, let's see when that is. That'll just be the rest, right? So from 0 to 1, it looks like velocity is positive, acceleration is negative, and then from 2 to 3. So from 0 to 1 and 2 to 3. And when you put those two sets together, you get the whole interval, other than at the points where, of course, acceleration or velocity is 0. Okay, let's make a t-table for time and position, and then we'll graph the schematic on this line graph here. Okay, so using my calculator, I found t and s of t. Oof, let's try that again. That's better. And I went 0, 1, 2, 3, 4, and 5. I went the first 5 seconds. Okay, so position, of course, was t cubed minus 6t squared plus 9t. Okay, I would, if I were you, type in that for y1, and then use your alpha trace y1, which will bring this up, and then in parentheses put each of these t values. So when I put them in, I got a 0 and a 4 and a 2, 0, 4, and then all of a sudden a 20. So let's look at what the schematic looks like for this graph. Okay, so this will be position, as is labeled here. These are the positions. So time is not part of this, but we could plant that within the graph, giving it a second part of its ordered pair. Okay, so at time 0, location is 0. Okay, and then at time 1, location is 4. So that means the particle, its velocity is positive, is positive from 0 to 1. Okay, so to give it some direction, I'm just going to put some arrows on it. Okay, so this was 0, 0. This was 1, 4. Okay, and then the particle turns around and comes back to 2, 2. Okay, I'm going to put that point there, 2, 2. And then 3, 0. So the velocity from time 1 to 3 is negative. And then the particle turns around and starts accelerating off in the other direction. So then it heads at time t equals 4. Its location is 4. And then at time t equals 5, its location, its position is 20. So obviously this particle is starting to take off in a cubic motion. Okay. And of course, then we can see what's going on here. Okay, let's continue on onto page 2. Let's talk about the squirrel. The squirrel back in 2010. Go ahead and look at the graph. Take a look here. We've got the graph of velocity. So anywhere the graph is above the t-axis, right, that means the squirrel is moving to the right on what ends up being this horizontal wire connecting two buildings. Okay, at t equals 9, the squirrel gets confused and thinks, should I go back? So it starts heading back, right? And then at t equals 15, it says, nope, I want to go the other way, back to building B. All right, so velocity in the positive direction, velocity in a negative direction, velocity back in a positive direction. So the squirrel makes choice at 9 seconds and at 15. Who knows? Maybe there's a condor flying above and misdirects it. Anyways, before I digress too far, let's read the problem. The squirrel starts at building A at time t equals 0, travels along a straight horizontal wire connected to building B for 18 seconds or minutes, maybe, I don't know, it doesn't give us units. The squirrel's velocity is modeled by the piecewise linear function defined by the graph above. At what times in the interval, if any, does the squirrel change direction? Oh, we already talked about that. So v of t equals 0 and changes sign at t equals 9 and 15. Now, be careful. This word right here, change direction, or that phrase, is important. Change direction means change sign. Now, if it said, when is the squirrel at rest? I mean, in this case, both of those places as well. But at rest could mean stops and then continues to head in the same direction. Okay, so be careful for that. All right, part D. We skip all the way to D because the other parts are not applicable, at least at this point in the course. Write expressions for the squirrel's acceleration, velocity, and distance from building A that are valid for 7 to 10. Okay, so we're not going to do distance because we don't necessarily have that skill quite yet. We're going to have that after chapter 5, I believe. Okay, so let's write an expression for velocity and for acceleration. Well, velocity on this portion of the graph is going to be the equation of that line. So I'm going to pick a point on that line, and I'm going to find the slope of that line. This point right here is 9, 0. And the slope of the line will equal, I could take any 2 points and find the slope. So I'll take 9, 0 and 7, 20. So 0 minus 20 over 9 minus 7. Okay, so our slope comes out to be negative 20 over 2. So the slope of that line is negative 10. Okay, so v of t, first I'm going to use point slope form here. So point slope form would be y minus y is equal to slope, negative 10, x minus x. So I'm using the point 9, 0, and I'm using the slope negative 10. Now, of course, this will just disappear, and if I distribute a negative 10 to both of those terms and come back to the variable t, I'd have negative 10t plus 90. So this would be an expression for the velocity, which would be valid between the times 7 and 10 for the squirrel. Now, the acceleration, of course, is the slope of the velocity, or the derivative of the velocity. Therefore, acceleration would simply be the slope of that line. All right, there's your acceleration showing up, and you get negative 10. Okay, let's continue with example 3. This is an AP example as well. It's no calculator example. Let's continue. So I have x of t, which is a position function, equal to 2t e to the negative t. It says the particle is at rest when t equals what? Well, particle is at rest when x prime of t equals 0. So let's find x prime of t. Of course, we got to use the product rule here, where we got the first function and the second function. So the derivative of the first is 2 e to the negative t plus the first function times the derivative of the second. So a derivative of e to the negative t is e to the negative t times the negative 1. All right, so I'm going to rewrite, clean this up into a form that will be more pleasing to t e to the negative t. And I'm going to set this equal to 0 and solve, but first I'm going to factor the left side. So I'm going to pull out a 2e to the negative t. That leaves me with 1 minus, what would that leave me with? 1 minus t. Look at that. Okay, now this expression, 2e to the negative t, will never equal 0. Never, never, ever equals 0. However, this expression can, clearly. So 1 minus t equals 0 when t equals 1. Look at that. We got ourselves an answer. Okay, let's continue with a couple more AP examples. Good old 04. Calculator portion. Particle moves along the y-axis so that its velocity at time t is greater than or equal to 0 is given by v of t equals this gross function. Clearly, when you see this, this would indicate likely a calculator question if you weren't looking above at the instructions, okay? At time t equals 0, the particle is at y equals negative 1. Note that tan to the negative 1x is equal to arctan of x. Okay, so part A is asking for the acceleration of the particle at time t equals 2. And since v prime of t, as we know, is equal to a of t, I'm going to use math 8. Okay, and I'm going to put v of t in as y1. Okay, and I'm going to sub in terms of x, and I'm going to plug in y1, and I'm going to evaluate at x equals 2. And according to my calculations, I seem to have misplaced my calculations. There we go. A at 2, okay, or the acceleration at 2, which is what we're calculating right here. It's the derivative of velocity located at 2, ends up being negative 0.133. Negative 0.133. Okay, so there's our acceleration at time t equals 2. Part B says, is the particle increasing, the speed of the particle increasing or decreasing? So is it speeding up or is it slowing down? Give a reason for your answer. So we already know acceleration is at time 2 is less than 0. Let's find the velocity at time 2. That comes out to, using your calculator, to be negative 0.436. So since a of 2 is less than 0 and v of 2 is less than 0, then the particle, all right, is, would that be speeding up? Speeding up. All right, 2011. Again, it looks like a calculator portion. This is a couple of really nasty functions. And be careful, when I first looked at this question, I thought this was e to the 1/4. That's a t. That's a t. That's a t. Okay, so be careful. Very similar to the last question, it's asking, is the speed of the particle increasing or decreasing? So we want to know, is it speeding up or slowing down at t equals 5.5? So what I did was I put v of t in for y1, and I put a of t in for y2, y2. And using alpha trace, I pulled up y1, and I plugged in 5.5, and alpha trace y2, and I plugged in 5.5, and I got myself two answers. The velocity at time t equals 5.5 was negative 0.453, and the velocity, or the acceleration at 5.5 was negative 1.359. Therefore, we could say the particle was speeding up, or the speed was increasing at t equals 5.5 because v of 5.5 and a of 5.5 have the same sign. All right, guys, that is 3.6 day number 2. See you in the next video.